Swayam Prabha. Digital India. Educated India.
Welcome to Lecture 5, Numerical Problems, Part 1. So, let us move to the question. So, the operating conditions, the temperature limits, that is the evaporator and the condenser temperature are same. The refrigerator uses R134A as the working fluid and operates on an ideal vapor compression refrigeration cycle between -18 and 32 degrees centigrade. If the flow rate of the refrigerant is 0.05 kg per second, so this is also the parameter is same compared to the previous two numerical questions. Determine the rate of heat removal from the refrigerator space and power input to the compressor, rate of heat rejection to the environment and COP of the refrigerator. Assume the condition of the refrigerant to be dry and saturated. Here there is a difference. The refrigerant is dry and saturated at the inlet of the compressor. So the state point 1 and 2, there will be change in the state point, because in the previous two problems which you have solved, the first one, both inlet and outlet of the compressor, the state of condition of refrigerant is wet, and in the previous problem it is wet at the inlet of the compressor and 2 at the state point 2 is saturated for the previous problem. So first let us plot the TS diagram and then the pH diagram, so that it will help the learners to understand easily and in a better manner. Temperature on the y-axis and entropy on the x-axis. So the condition of refrigerant at the inlet of the compressor is dry and saturated. So that means state point 1 should be marked on the saturated vapor line. So this is state point 1. This is 1. Let me redraw it again. So state point 1, this is isentropic compression 1 to 2. I think the letters are not clear. Let me plot the process again. Isentropic compression 1 to 2. Then we have the condensation process from 2 to 3. So let us mark this intersection point as 2 dash. 2 dash. This is the work of compression. And from 3 to 4, throttling process. Then we have the evaporation. So if you extend the isothermal line to isothermal line, so here it is evaporator temperature and here it is condenser temperature. So let me plot the pH diagram. So state point 1 is in dry and saturated. Here also it will be on the curve. So this is state point 1. Sorry, state point 2. This is after compression. This is state point 1. Remark is like this. Process 2 to 3, condensation, then 3 to 4, throttling. So let us mark the heat transfer quantities. QC, QE. Similarly here also, this is QE, the evaporator heat load, and this is the condenser heat load. There is one work transfer quantity, that is work is done on the system. Compressor is a power absorbing device. So work is done on the system. I think point 1 is not clear, so let me mark it here. Point 1. And this will be 2 dash. This will be 2 dash. Now if you, this is the isobaric line. So here pressure at 1 will be equal to pressure at 4. P1 equal to P4. And similarly here P3 will be equal to P2. P1 and P4 will be equal to the evaporator pressure, and P3 will be equal to P2, which is the condenser pressure. So let us write the data given. So R134A, there is no change compared to the working fluid which we have used for the previous 2 numerical problems. Mass flow of the refrigerant is given, which is also same, 0.05 kg per second. No change in the evaporator temperature. So TE is equal to T1 is equal to T4, which is equal to minus 18 degrees centigrade. Condenser temperature is 32. If you see the temperature entropy diagram, Tc is equal to T3, which is equal to, instead of T2, it is T2 dash. Because when the condition of refrigerant at the inlet of the compressor is dry and saturated, so the point 1 is already lying on the saturated vapor curve. So when the refrigerant is compressed, the state point after the compression process is completed, it will be in superheated condition. So let me have a quick recap. The region which is towards the left side of the saturated liquid line, it is called subcooled region. The region which is towards the right side of the saturated vapor curve is called the superheated region. So here T3 equal to T2 dash, which is equal, this point is T2 dash, which is equal to condenser temperature. The temperature of the refrigerant after it is compressed, that is the superheated condition, is not given, so which we have to determine. So T2 is not given. T2 is not given. This temperature need to be found out. So this is the, if you extend this line, this is T2, which is unknown. Let us go back to this one diagram. So if you see the given, this is the TS diagram and the PS diagram. So since I am explaining, I have just plotted it again, which I will be doing it for all the numerical questions. So this is the data given. So let us calculate the properties which can be taken from the tables directly. Then we will calculate the enthalpy or the parameters which cannot be found from the table. So let us start from state point 1. I think I have used the second page. So let me just change this one, or okay, let me complete this one. So let us take state 1. So I will write here continued in let me try to complete in the next slide itself. If it is not sufficient, I will use the previous one. So state 1. State 1 is in saturated vapor line. So directly we can read the enthalpy value, entropy value from the tables. So from tables, that is R134A. The temperature at 1 is the evaporated temperature. So at minus 18 degrees centigrade, yes, entropy at 1 is equal to vapor entropy, which is equal to S1 is equal to Sg. So let us go back to the tables. This is minus 18. Sg value is here. It is coming here. Vapor entropy 1.7399. (1.7399) kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Let us take the enthalpy value also. H1 is equal to, that is also vapor enthalpy at the same temperature, that is minus 18 degrees centigrade. So this is liquid enthalpy, this is vapor enthalpy, 387.89. 387.89. 387.89 kilojoule per kg. So we have found the enthalpy at state point 1. Next, if we want to find out the enthalpy at state point 2, we should know the temperature, and that state point 2 is in superheated condition. So the enthalpy value cannot be taken directly from the tables. We need to calculate. Of course, enthalpy at 3 can be easily determined. Can be easily found taken from the tables, which is equal to H4. And here, before finding the enthalpy at state point 2, that is H2, we need to find out the temperature at T2. Process 1 to 2, let us consider, it is a isentropic process, isentropic compression. Therefore, S1 is equal to S2. S1 is equal to S2. S1 value we have found, that is Sg, which is 1.7399. So, which implies S2 is equal to 1.7399 kilojoule per kg Kelvin. Since S1 is calculated, is taken from table, from R134A table. Refer previous page. Refer previous. So S2 equal to 1.7399. S1 value we have taken and H1 value is taken. Now we are going to find out. Yes, since S1 is equal to S2, therefore whatever the value of S1 will be equal to S2. Now I will be using this relation in order to find out the temperature T2. S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. We will be using this relation. S2 minus S2 dash is equal to Cp of vapor into ln of T2 by T2 dash. In this, T2 dash is given, which is nothing but T2 dash is equal to, if you see the diagram, T2 dash is equal to T3, which is nothing but condenser temperature. So that is known. S2 we have found, S2 we have found, that is nothing but S1. So this is known, this is given in the problem, which is the condenser temperature. So we have to find out Cp of vapor and S2 dash. Okay, S2 dash. If you look at the TS diagram, 2 dash is lying on the saturated vapor curve. The corresponding temperature is condenser temperature, which is 32 degrees centigrade. So I will read the S2 dash value directly from the table. S2 dash is equal to, that is vapor entropy at the temperature T2 dash, which is equal to T3, which is equal to condenser temperature 32 degrees centigrade. That is from R1348 table. 134A table. So corresponding to 32 degrees centigrade, whatever the vapor entropy is there, that is the value of S2 dash. So you can read this value from the table. S2 dash is equal to, this is 32 degrees centigrade. SG value is 1.7142. kilojoule per kg Kelvin. So if you see here, S2 dash is 1.7. This is what I have. This is the value which we have taken from the table. Now Cp of vapor also can be taken from the same table corresponding to 32 degrees centigrade. And the last two columns are, this is Cp. This is Cp of liquid, and this one is Cp of vapor. So corresponding to, anyway, this is the first page. So this is minus 18. So let us go to the next page where 32 degrees centigrade is there. So this is Cp of liquid and this is Cp of vapor. So corresponding to 32, it is 1.058. 1.058. The condition of refrigerant is vapor. So we have to take the vapor specific heat capacity. And Cp of vapor is equal to 1.058 kilojoule per kg. This is the value which I have taken and which has been mentioned in this slide. 1.058. Actually, if we know the temperature T2 dash, then the Cp value we have to take the average of T2 and T2 dash. Since it is not known, since the T2 dash is unknown, so we have to take the value corresponding to the condenser temperature, which is T2 dash. So substituting these values in this equation, substitute the values of S2 dash, Cp vapor values. Let us take this as equation number 1. In equation 1, so you will get, so now this is also known, S2 minus S2 dash, 1.7399 minus S2 dash, 1.7142. This is on the left hand side. Cp of vapor is 1.058 into ln of T2 is unknown, T2 dash is 32 degrees centigrade. Here we have to convert the centigrade into Kelvin. We should not substitute the temperature in terms of degree centigrade. So 32 plus 273. 32 plus 273. That will come in the denominator. So solving, we will get T2 as, so if you see the calculated value of T2, it is close to 40 degrees centigrade. So exactly it is 39.5. That is T2 is 3112.5 Kelvin. 312.5 Kelvin. So which is nothing but 39.5 degree centigrade. So this is the value of T2. This is the value of T2. This will be continued in the, this is slide number 13. Continued in slide 11. Okay, so this will be, I have not used, I left one slide before. So this is continued from slide 13. Continued from slide 13. Now we have found out T2. So now we have to find out the superheated enthalpy at state point 2. Okay, enthalpy at state point 2. So using this formula, see H2 equal to, state 2 is in superheated condition. So superheated enthalpy is equal to saturated enthalpy plus Cp of vapor, because the condition of refrigeration is vapor, into delta T. So you will use this relation. Enthalpy at 2 is equal to, if you go to the diagram, enthalpy at 2 is equal to, superheated enthalpy is equal to saturated enthalpy plus Cp of vapor into delta T. H2 dash plus Cp of vapor into delta T. So this is equal to H2 dash plus Cp of vapor into delta T is T2 minus T2 dash. T2 minus T2 dash. Now here, since we know the value of T2, Cp value, I will take the average of T2 and T2 dash, where Cp of vapor is at average of T2 plus T2 dash by 2. If you go to the T2 is 32. So already we know the Cp of vapor 1.058. You can, okay, sorry, the average of the temperature. So first let us find the average of the temperature. So T2 is 39.5 degree centigrade and T2 dash is 32 divided by 2. So if you take, it is approximately 36 degree centigrade. 36 degree. That is the average temperature. Now the Cp value to be found out corresponding to 36. Corresponding to 36. So if you go to the table, this is 36, this is 36, and the last column is specific capacity of vapor. So 1.088 from R134A table at 36 degrees centigrade, Cp of vapor is equal to 1.088 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Now Cp of vapor is found. T2, T2 dash are known. Once we know the enthalpy at state point 2 dash, we can find out the superheated enthalpy at state point 2. So this is like how we found S2 dash, we can find this one. So if you see the condition of refrigerant state point 2 dash, it is saturated vapor corresponding to condenser temperature. So H2 dash is equal to Hg at 32 degree centigrade, which is the temperature of T2 dash is equal to T3 is equal to Tc from R134A tables. 134A tables. H2 dash is equal to Hg corresponding to 32 degree centigrade. Corresponding to 32, this is liquid enthalpy, this is vapor enthalpy, 415.9. So H2 dash comes to 415.90 kilojoule per kg. 415 kilo. Let us check the values. H2 dash is equal to 415 point. This is H2 dash 415 point. Now substitute the values. Substitute the values. Let this be equation number 2. Substituting H2 dash Cp of, sorry, this be equation number 2. Cp of vapor, comma, T2 dash T2, because T2 dash is given in the problem. Okay, so you can, that also we can write. So we will get H2 is equal to enthalpy at state point 2 is 424.1, 424.06 kilojoule per kg. 424.06 kilojoule per kg. So I will be continuing this problem in the next lecture. Thank you.